we'll go for understanding the implementation of the threaded binary tree. Program for implementation of in-ordered threaded binary tree and perform this operation: insertion, deletion and display of the tree. So this is what the implementation we're going to discuss now. So you don't have lab program on this, there is no lab program on this, but this is the implementation which you should know. Okay, so now for writing purpose I'll try to open this in the Microsoft Edge. Okay, till that time, till it gets opened there. So we'll continue with this. Now, as already told, to represent a node of a threaded binary tree in the memory, so you got to define 5 fields. One is the data field, or the info field. Another one is LTH, which is the boolean value, which either we store 0 or 1. Okay, if the left thread exists, okay, then this will be 1. If there is no left thread, we make it as 0. So I hope you people know, because we have already constructed the threaded binary tree using the memory representation format, that is the 5 field format. And similarly, this is RTH, which again stores the boolean value 0 or 1. And then left and right, which is a self referential pointer. Left, which holds the address of the left subtree, and right again, which holds the address of the right subtree. Okay, and this, while writing the structure itself, we have applied the type def definition. So note, so in case if I want to declare any pointer to the struct BST, binary search threaded tree, I can just go for creating it as node star some variable name. And in the previous class you also understood building the threaded binary tree by using a dummy node. Okay, initially we are going to create a dummy node, and to that dummy node we are going to attach the actual root node. So similarly, so here we have created a dummy node. Okay, node star dummy. This is the dummy node, the starting node which we are creating, and just under this dummy node we go for attaching the root node. Okay, either as the left child to this or as the right child to this. Okay, that is what the structure, this is what the structure that is used in order to represent a node of a threaded binary tree in the memory. Okay, I think it is opened. Yeah. Okay, so you understood this is the dummy node what we are creating, and next is inside the main function. So as usual we have a variable for choice and then key. Okay, and then character answer is equal to n. Okay, because it will ask every time you execute this for loop, this program, it will ask you whether you want to continue with one more execution or not. If you say no, it gets terminated. Otherwise, it will continue with the second execution or one more execution. And similarly, so along with this dummy pointer, which is a pointer to this structure, struct BST, we also have other pointers like root, temp, and parent. So again, these are all the pointers to my structure BST. And these are the function prototypes. So one function we have with the name create, and what it is returning, it is going to return the address of a node in the binary threaded binary tree, and what it takes as argument is again the address of a node in the threaded binary tree. So one more prototype, function prototype is search. We have a method with the name search, or the function with the name search, and again the return value from search is also of type node star. That means search also returns the address of the node which you are searching for, if it exists. And similarly here, once again what we are passing is as argument pointer to the node, integer, so which you want to search. Okay, and then this is the node again. Okay, so dereferencing double star we have written, dereferencing it twice. We'll understand when we go to this implementation, search function implementation. And similarly, in order function is also there. Okay, so because you already know, okay, for constructing the threaded binary tree, in order traversal is very much essential, because whenever there is a null pointer, so if there is a null pointer in the left child of a node, so then what you have to do in the left link of a node, so then you have to create a thread to the node which is previous to the node which is carrying the null value in the left link, so that is what does the in order is. Okay, in order traversal is necessary. And similarly, if there is a null pointer in the right link, then you should add a thread from that null pointer to the node which is very next to the node which you have considered. Okay, and then delete operation. Okay, one more function prototype for deleting a node from the threaded binary tree. So next, this is the menu option what we are displaying. Create, display, search, and delete. So these many options we have. We read it to the choice, and then here switch choice. So if I am creating the threaded binary tree for the first time, it comes to case 1. So initially it will make the root node as null. Okay, and then inside the do while loop, because I want this statement to these statements to get executed at least once, irrespective of the condition. So inside the do, so I'm calling create root. Okay, calling the function create. So we'll just go to the create, and this is going to repeat as long as your answer is yes. The moment you say the answer as no, okay, so it will stop creating the tree. Now we'll go to the create function and understand it. Yeah, so here is the create. Initially the root what we are passing here is null initially, because root is initialized to null, and then here again I have a function called as insert, and then what I'm passing is again node and node. So let us go to the function insert here. So insert root node, and the other one is the new node which I want to insert. So I'm checking whether the data field of the new node, okay, is lesser than the data field of the root node. So if it is lesser, so then what is that you have to do? Root arrow LTH should be made as if root arrow LTH is equal to 0, you make root arrow LTH is equal to 1, because the data field of the new node which you want to insert is less than the data field of the root node. So then which position it has to take? So the new node should take the position in the left subtree of the root node. So now again I'm checking if root arrow LTH, this boolean value, if it is equal to 0, you got to make it as 1, because it's going to have the left child now. Okay, this one. So new arrow left is equal to root arrow left. Okay, in the left field, okay, or the left link of the new node, what is that you're going to store? The root arrow left. That is the address which is present inside the left field of the root node. And similarly new arrow right is equal to root, and root arrow left is equal to new, and root arrow LTH is equal to 1. Okay, so something like this. So if this is your root node, I'm writing here, say this as some value, say 8. Okay, and this is the left link, this is the right link, this is LTH, and this is RTH. Now what is that I'm doing? If root arrow LTH is equal to 0, I make root arrow LTH is equal to what? 1. So this one I'll make it as 1, and now I go for inserting the new node here, and root is pointing to this. So root is pointing to this. I have the new node created, and who is pointing to this? New is pointing to this. So new is pointing to this. Say the data field of the new node is 7, which is less than 8. Okay, so new arrow left, this is new arrow left, is equal to root arrow left. root arrow left is this, which is okay. 1 second. So new arrow left is equal to root arrow left. So root arrow left is holding this. That means root arrow left. Yeah, what is here? Address of this node. It should be 1 minute. Create. So insert. Oh, sorry, I should not come here. Okay, just a minute. I'll erase this because that was the function prototype. First we got to create the node. We have not created the node itself. Yeah, this is the function prototype. So function prototype for the insert, and here node new pointer I am creating. Now allocating the memory for the new node. So let me write here. So the memory is allocated for the new node. So this is not the function call, this is the prototype, don't confuse. Even I got confused with the same. Now this is new. New is pointing to this. So let me say the data field is 7. This is the left field, right field, this is LTH field, and this is RTH field. So now after that, so new arrow left is equal to null. So this I am storing null, and new arrow right is equal to null. This also null, and new arrow LTH is 0. So this either you can go for storing 0 or false. So I'll go for storing 0, boolean value 0, and then even in RTH also 0. Hope this is clear.
Yes, sir.
Okay. Now
Yes, sir.
enter the element. So I'm reading the element, okay, and directly storing the element here. So this is enter the element. I've entered 7, and 7 is directly read into this position. Now I'm checking if root is equal to null. Yes, root is null. Okay. So root is equal to new. This is the first node what we created. So we make root also to point to this. So hope this statement is clear.
Yes, sir.
Okay.
Yes, sir.
Root is also pointing to this. Okay. Root is also pointing to this. Next. So we are creating the dummy node. So this is the root node now. Just before this, we should have a dummy node. So if you have dummy node, those dangling pointers which I explained you in the previous class, so even that can also be avoided. Now, so I am allocating the memory for the dummy node. So here the dummy node gets created, and who is pointing to it? The pointer with the name dummy. So dummy. So dummy is pointing to this, and just observe now. So in the data field, what I am storing is minus 999, because something I have to store in the data field. So I am taking minus 999, assuming so I don't give minus 999 as the data field for any of the node. Minus 999. Okay. Next. So dummy arrow left is equal to root. So this is the left link, this is the right link, this is RTH, and this is LTH. Now what I am doing now, dummy arrow left is equal to root. I am storing the address of this node here. Hope that is clear. So for your reference, you can open the threaded binary tree which I have constructed using this memory representation for a node. So now this link is established. That means address of this node is stored here, dummy is pointing to this, root is still pointing to this, nav is also still pointing to this. Okay. Next, root arrow left is equal to dummy. Okay. Root arrow left is this. Correct, right? Hello.
Yes, sir.
Okay, since so this is the left child now, correct, no? To the dummy. So now root arrow left, this was null now. Now this null I'm making it as a non-null pointer. How to do that? Root arrow left is equal to dummy. So let me erase this, and I'm creating a thread from here to here. Okay, and then root arrow right is equal to dummy again. So this was a null pointer. Okay, now again I erase this and I'll convert it into a non-null pointer by saying root arrow right link is equal to dummy. Is that clear till here?
Yes, sir.
Okay, next. So if root is equal to null, if that is the first node which you are creating, you know, this is what we do. So if if root is not null, okay, then what we do? So we go for so we go for this else part, and we call insert root and then new. Okay, let me take again create. Okay, so answer is yes. It will ask you whether you want to add one more node. Say yes, then again it will make a call to create root. So we come here. So do you want to enter more elements to the tree? So you have to say yes. Okay, so then again it comes to create here now. So create a new node. So new was pointing to this. Let me erase this. Now new is no longer pointing to this. A new node is created now again. So new is pointing to this. So new is pointing to this, and let me assign some info field to this. So yeah, let me start from here. So new arrow left is equal to null. So I'm storing null initially here. New arrow right is equal to null, and then new arrow LTH is 0, RTH is also 0. Next what I do, I go for reading the data field for this node. Let me take the data field as 6. Okay, next. I'm checking whether root is null. So root is not null right now. Root is pointing to this. Now we should go for the else part and make a call to the function insert root new node. So root we are passing, address of the root node we are passing, and we're also passing the address of the new node that is created. Okay, now we'll go to insert function. Yeah, this is what is insert. Okay, now here I'm comparing the data field of the new node with the data field of the root node. So data field of the new node is 6 and the data field of the root node is 7. 6 is less than 7, condition is true, and then I go for checking whether root arrow LTH is equal to 0. So if you look into this, root arrow LTH is this and it is 0. Yes, condition is true. Now we get into this. And what we do, new arrow left is equal to root arrow left. Observe here, new arrow left is this is equal to root arrow left. Okay, now what is there in root arrow left now? Now what this is storing? So if I take the in-order traversal, so 6 will come before, right? So first 6 and then 7 will come. Towards the left side of 6, what will be there? Nothing,
sir.
And the left link of the new node should have a pointer to what? The dummy node. Hope it is clear.
Yes, sir.
Okay, so same thing what we are doing here. So root arrow left is equal, new arrow left is equal to root arrow left. Root arrow left is nothing but what? Root arrow left is nothing but your dummy node. Okay. From here, so we are creating this null, we are erasing, and then creating a thread from here to this. Okay. Next, new arrow right is equal to root. So new arrow right is equal to this one. New arrow right is equal to root. It is pointing to this. Okay. Now root arrow left is equal to new. If I go up, so root arrow left, where was it pointing? It was pointing to this. Okay, dummy node. Now I don't want it to point to the dummy node, since the root node has got the left child. So the left link of the root node should point to its left child. I'll erase this now, and then from the left link of the root node there is a pointer to the new node. Okay, and next, root arrow LTH should be made as 1, because it has got one left child now. So this boolean value 0, so I should update and make it as 1. So you just try to compare this with the one example which we have solved in the previous classes. Hope you people understood?
Yes, sir.
Okay. See, in the right link, of 6, we have a pointer to what? A thread created. From the right link of 6, there is a thread created back to the root node. Why? Because if I write the in-order traversal for this, okay, so first is 6 and next is 7. Now, when I take 6, towards the left side of 6, there is no node. That means the left link of 6 should point back to the dummy node. And when I check the right side of 6, there is 7. That means the right link of 6 should point back to the root node. So that is what we have written. Any doubts till here?
No, sir.
Okay. Now I think we'll take one more node, just one node, and we will go with the create. Okay. I'll take just one more node. Say again, I'll say yes. It will ask me here. Do you want to enter more elements? Say, assume I have entered yes. Okay. Again, it makes a call to create. What create will do? It goes for creating a new node. Again, one more node is created. Let me reduce the zooming. Okay. So this is one more node that is created. Now I'll take 8. Okay, 8 is bigger than the data field of the root node. Okay. So this is the right field, left field, LTH and RTH. Now initially when the node gets created, both left field and right field, they will be having the null pointer. Okay. And who is pointing to this? New is pointing to this. Now, so new is no longer pointing to the node 6. Now it is pointing to the node 8. New is pointing to this. Okay. Next, I check again after reading all these things, setting the RTH to 0, LTH to 0, left link to null, right link to null, and the data field of the new node as 8. I check if root node is equal to null. So root node is not null, because the root node is pointing to the root node, and there are two nodes which is right now existing inside the threaded binary tree, and this is the new node which I need to insert. So this condition is false now. Again it will go to the else part and make a call to insert a new node by passing the address of the root node. So we are passing the address of this node, and we are also passing the address of the newly created node. Now we'll go to the insert. So again I'm checking whether the data field of the new node is lesser than the root data field of the root node. So data field of the new node is 8 and root node is 7. 8 less than 7, condition is false. So that means this new node will not take the position in the left subtree of the root node. So it should be inserted towards the right subtree of the root node. So again this condition. So the next if condition what I am checking is checking whether the data field of the new node is bigger than the data field of the root node. Yeah, this condition is satisfied now. And then I go for checking whether the RTH field of the root node is 0. So when I check the RTH field of the root node is 0, it is true. That means so we don't have any right child for this root node still. Okay, and this shows that so the new node 8 should be inserted towards the right side of or inserted as the right child of the root node. Now we are here now. Okay, this is also true. Now what I do now, new arrow right is equal to root arrow right. Okay, in the right link of the new node I am storing the address of what the dummy node. So if you just look into this, the right field of the root node, it was pointing back to what, the dummy node. Now what is happening, this null pointer I am erasing in the new node and creating a thread from here to the dummy node. Is this clear?
Yes, sir.
Okay, so now so this is done. New arrow left is equal to root. New arrow left is equal to root. So if you start writing the in order sequence for this, what it will be, just tell me the in order
6,
sequence.
7, 8.
6, 7, 8. So 8 is the node which I am considering now. Now the left link of 8, what it should have, it should hold the address back to the 7, because towards the left side of 8 what we have is 7. So same thing what we are doing here. So new arrow left is equal to root. New arrow left is equal to root, means it will a thread will be created from here to here. I'll erase this null pointer. And then from here a thread goes back to root node. And this is null again. Okay, so because after 8 there is nothing, that means the right link of 8 should point back to the dummy node. So hope it is clear, the implementation of creating a threaded binary tree.
Yes, sir.
Okay. So now we'll go to the next case. So case 2, that is display. Okay. So we come to case 2 here, display. Before displaying, we check whether the root is null. If the root is null, we just say the tree is not created. Okay. So if the root is not null, then we go to the else part, and tree is, we make a call to in order, because we perform the in order traversal and then we go for displaying the content of the entire threaded binary tree. Okay. Let us go to the in order, and what we are passing is the root. This is search, delete, in order function here. So what we passed is root, and that root gets copied to temp. Okay, I'm checking temp not equal to dummy. Okay, so right now root is not equal to dummy, because root is pointing to the next node after the dummy. And next what I do, I check while temp arrow, okay, LTH equal to 1, as long as the temp arrow LTH is equal to 1. So I keep traversing towards the left side, because I am interested in displaying the nodes in the in order traversal. Okay, So I keep traversing the left subtree, and then I go for printing the data, okay, and then I just again check whether temp arrow RTH is equal to 0. So if it is equal to 0, then I keep traversing the right subtree, and if temp is equal to dummy, so return, otherwise go for printing the data. Okay, so this will go for printing all the nodes of the threaded binary tree in the in order traversal. Okay, so you can go for using this. This is a non-recursive function, or else you can also go for using the recursive function. Now, recursive function is what? So first recursively traverse the left subtree, and then visit the root, and then recursively traverse the right subtree. Okay, so the same recursive function what we have understood earlier, so the same thing can be applied here also, but this is a non-recursive function what we have written. Okay, hope you understood.
Yes, sir.
So the same in order function what we have understood, the recursive definition what we have understood, so same thing can be written here. Okay, this is a non-recursive function what we have written. So that is what is in order function for displaying the threaded binary tree in the in order sequence. So, and similarly, sir, can we display it in the pre-order and post-order traversal also? Yes, you can go for. So it's the same function what you have understood. The recursive function for in order pre-order display and post-order display can also be used. So that is the case 2. Next is case 3. So case 3 is searching. So even we have performed searching in the normal binary tree, searching for a given key. Now the same thing can also be performed on the threaded binary tree. Okay. Now case 3, search. So now it is asking you to enter the key element to search, and the element which I need to search, I'm copying it to the variable key and then making a call to search function by passing root. So I'm passing the root, address of the root, so the key element which I need to search, and then parent I'm passing. So parent initially, I think it is initialized to null. I'll show you here. Okay, it is not initialized to anything. So parent is another pointer what we are passing. Okay, let us go to the search function now, the definition of the search function. Yeah, so search function is like this. So temp, so this is double star because it acts as a pointer to the pointer. Okay, so temp is another pointer which we have taken to the structure BST, and then so temp is equal to root. So I'm making temp also to point to the same node where root is pointing, and using temp I'm checking whether it is equal to dummy. So I'm checking whether temp is same as the dummy node. So if it is not true, then I go for comparing the data field of that temporary node with the key element. So if it matches, I say the element is present. Okay, and I also go for displaying the same element and return temp. So if it doesn't match, then what I'm doing, so parent is equal to temp. Okay, so parent is equal to temp. That means parent will go for pointing to the same node where temp is pointing, and then I check, so temp arrow data greater than key. Okay, so checking whether the data field of the temporary node is greater than the key element. If it is true, then I keep traversing. I make temp to follow or traverse the left subtree. Otherwise, I make the temp to traverse the right subtree and then return null. Okay, so this process we repeat as long as temp is not equal to null. So when temp is going to equal to this, temp is going to equal to dummy. So the moment it reaches the leaf node, okay, when it reaches the leaf node, so one of the leaf node should have its left link, as what, pointing back to the dummy. Okay, so and there we stop it. And similarly, if it has traversed the right subtree, and one of the leaf node in the right subtree will be having a pointer back to what? The dummy node. So that when it reaches back the dummy, we just say stop iterating and then return what? Null. That means the element is not found. Okay. So if the element is found, it get displayed here, and then it is going to return you temp. Hope you people understood with this.
Yes.
Okay. So this is the search, and we have delete as well. So, and previous classes I explained you how to delete from the nonlinear data structure trees, binary trees. So there are three options for deleting. Deletion can be done in three ways. One is deleting the leaf node, that is the first type, which is the most simplest thing, and deleting a node with what? One child, either the left child or the right child, and deleting a node with both the childs, left child also and right child also. Can anyone tell how to perform the deletion of the node which is having either the left child or the right child? How do you establish the link after deleting? So which traversal you have to consider for this again? In-order traversal. In-order traversal you have to take. Okay. So just try to recall that sequence what I told you people in the earlier classes. When you are trying to delete a node with one child, either the left child or the right child, so what you have to do, you got to see what is the in order, what is the node which is before the node which you are trying to delete. So that node should be replaced with this node which you are trying to delete. And similarly, if you are trying to delete a node which has got both left child as well as right child, you should go for replacing the node which you want to delete with the node which is the immediate successor to it in the in-order traversal. So that is what we understood. Okay. Now we'll go to the delete function here. Okay. Case delete. Yeah. Now what we are doing, we are reading the element that we want to delete. So reading it into key variable again. So now making a call to delete function by passing the address of the root and key. We'll go to delete now. Yeah. So delete. Now we have taken temp, parent, and temp successor, and this is the prototype. Such is the prototype again here, don't confuse. And yeah, the flag we are making it as 0, and we are making a call to the search. Before deleting, you got to search whether the key exists or not. Okay. Search, and then if the key element exists, okay, now what search is going to return? It is going to return you the address of that element, so that gets assigned to temp. Now I am checking if the node or the key which I want to delete, whether it is the root node itself. Okay, root is equal to temp. So then I say printf its root node which cannot be deleted, because if you go for deleting the root node itself, with whom you are going to replace it? So you don't have any option for replacing it. So then we stop here. We just display this message and we stop. So deleting a node with 2 children. So this is the case what I am checking. Okay, and later we go for checking deleting a node with 1 children. Now how do you check whether the node has got 2 children or 1 children? So you can make use of LTH and RTH for this purpose. If temp arrow LTH is equal to 1 and temp arrow RTH is also equal to 1, what does it mean? The node has got 2 children. Okay, then I make parent is equal to temp. Okay, temp was pointing to the node which I wanted to delete, and using that I checked whether the temp has got the left child and the right child. So if these conditions are true, so the temp has got both left child as well as right child, then I make parent to point to it. Okay, so after making parent to point to it, so I just make temp successor is equal to temp arrow right. Okay, finding in order successor. This is what we are doing. So I got to search the in order successor for the node which I am trying to delete. Now in order to do that, so temp successor is equal to temp arrow right. So that means temp successor is pointing to the next node. So say for example this is temp. So temp is pointing to this, and this has got left child and right child also, and who is pointing to this? Parent is also pointing to this parent. Since it has got both left child and right child, now what is it I have to do now? Now this should be replaced by this. I have to remove the info field what is present here, and I should put the info field of this node here. Okay, in order to do that, temp successor is equal to temp arrow right. That means temp successor is pointing to this, temp underscore successor. So hope it is clear.
Yes, sir.
Okay. Now,
Yes, sir.
so now to the in order successor of this node, who is pointing? Temp successor is pointing. Next, while temp successor arrow LTH equal to 1, that means even for this temp successor, if the left child exists, okay, flag is equal to 1 and parent is equal to temp successor. Okay, now where parent points? Parent which was pointing here, now it points to this. Parent is not pointing to this, so parent is pointing to this. And next, temp successor is equal to temp arrow left. Now we make this temp successor to travel the left subtree of this node, and temp successor is pointing to this, and its parent is pointing to this. Parent is pointing to this, temp successor is pointing to this. Okay. Next, and this process we repeat until temp successor as the left child. Okay. If flag is 0, that means if the condition is not true and if it doesn't go here, the flag will remain 0. And once the condition enters into this while loop, the flag will get changed from 0 to 1. Okay. If flag is 0, this is what I do. That means this itself, this is the only node, and this node I need to overwrite here. So the data field of the temp node, which is here, the parent node, should be overwritten by the data field of this node. So that is what I'm doing here. So temp arrow data. So temp arrow data, this field is equal to temp underscore successor arrow data. So the data field is just here. It's going to overwrite this data. Understood?
Yes, sir.
Okay. Next, temp arrow right. So parent arrow right. Parent is still pointing to this. Okay. So right field of the parent or the right link of the parent is equal to temp underscore successor right link. So what we do in the right link, so which was holding the address of this node. Now what is that I need to do? I need to make it hold the address of the right child of this particular node. So temp arrow right, this field is equal to temp successor arrow right. So here we have the temp right field of the successor field. This we write it to here, and then make parent arrow RTH is equal to 0. Now if flag is not 0, flag is 1, that means the control has entered into this while loop. What you have to do here, you have to come, and then temp will be pointing to this. Temp arrow data is equal to temp underscore successor arrow data, then make this. That means it add the left subtree or the right subtree. We have recursively traveled till there, and we are attaching. Understood now?
Yes, sir.
Okay, in order successor is on the left branch and it has to be traversed. You traverse it and you attach it to this. Okay, and similarly we go for deleting a node having one child. How to delete? So this is what, so we'll discuss this in the next class. Okay, so this is a very beautiful program and interesting program than compared to your normal binary search tree program. So please go through this and understand properly. Okay, so if you, while going through, if you get any doubts, please make a note of it. Okay, and you ask me when I come for the next class. And if you get time, try to execute also this. Okay, so a very beautiful program, so than compared to your normal binary search tree program. Okay, threaded binary tree is a very beautiful program. So we'll stop here and we'll continue in the Monday's class. So deleting this, deleting a node with one child, okay, we'll discuss in next class.